So we'll go with the next straight line mechanisms. Okay. So one of the most common forms of the constraint mechanisms is that it permits only relative motion of an oscillatory nature along a straight line. Okay, the mechanisms used for this purpose are called straight line mechanism. Okay, so whenever you want an output in a straight line, okay, the mechanism is considered such a way that if you just place one pen on that, and if you try to move that mechanism, the pen will mark in the straight line. Okay, so this type of mechanism is known as straight line mechanism. In that we have two types of mechanism which may produce exactly a straight line, means perfect straight line, as you draw in with the help of scale you get straight line, or it may get an approximate straight line, means just by freehand if you draw a straight line, how you get not perfectly straight. So like that also you may get straight line. So two types of straight line can be seen, exact and approximate. So we'll see both the straight line, exact straight line, approximate straight line now. So first we go with the exact straight line motion mechanism. So in this the principle adopted for the mathematically correct or exact straight line motion is described in the figure you can see. So let O be the point on the circumference of a circle, that is having the diameter OP. Okay, and OA is a type of chord, and B is the point on OA. Okay, just produced in such a way that O is extended to B, and OA and OB, OA into OB, if you take it as nothing but as a constant, and then the locus of a point B will be a straight line. Okay, that you can see there, B will be a straight line and perpendicular to the diameter OP. So this may be proved as follows. So you can see, you have to see that BQ, that color is shown there in pink color. Okay, that should move in a straight line in the form of BQ. Okay, so that type of mechanism will be a type of straight line here. So draw a BQ perpendicular to OP, that is joined from AP which is there. From there if you take a straight line BQ, that will be perpendicular to OP, that is extended, and join at join this AP. So the triangles will be getting, you will be getting two triangles here. One triangle will be, that is OAP, this one OAP, and another triangle will be getting OBQ. Okay, this triangle. Okay, so these triangles are similar. So therefore OA by OP, okay, OA by OP equal to OQ by OB. Okay, so from that you will be getting OP into OQ equal to OA into OB, and OQ is nothing but OA into OB divided by OP. Okay, so but OP is a constant as it is the diameter of the circle, therefore OA into OB is constant. So then OQ will be constant, hence the point B moves along the straight path BQ which is perpendicular to OP. Okay, so from this OA to OB, that is made constant, and that is nothing but BQ will have a straight line. Okay, so this is the just exact straight line mechanism, how it can be constructed. So let us see the mechanism now. So we have Pislier mechanism. Okay, Pislier mechanism is a mechanism that will have a straight line mechanism. Okay, so let us see the construction here. In the figure you can see it consists of O1 as a fixed link here. O1 is a fixed link, you can see that it is fixed. Okay, and the other straight links, that is O1 to A, then O to C, okay, and O to D, this one, and then this AD, and then BD, this one, that is or DB, then BC, this one, and CA are connected by the turning pairs at their intersection as shown in this figure. You can see this. Okay, they are all connected here, and the pin at A, this one, is constrained to move along the circumference of a circle. You can see this O1A is nothing but the type of center. O1A is a radius here, and you can see that A can be moving the path of the circle, entire circle. Okay, and is constant to move along the circumference of a circle with the fixed diameter OP. Okay, so diameter with fixed diameter OP. This is the diameter, entire diameter OP. Okay, by means of this link O1A. So O1A becomes the nothing but a radius. So in this figure, AC equal to CB equal to BD equal to DA. Okay, so all these are equal. Type of rhombus you can see. Okay, that is ABCD, all things AC, BD, all this are all equal length. Okay, and then OC length is equal to OD length. This is from here to here OC, and then O to D, both are equal, and then O to O1, this length is equal to O1A. This length should be equal to this length O1A. Okay, so if this type of mechanism is considered, so what will happen when the rotation is there from O1 to A in the circular path? This point B and B to Q, this will form a straight line. You can see dark pink color here. So this will move in the straight line path. So this is going to rotate here, and this will give you the straight line path. Okay, and you can get this by taking again a equation. So it may be proved that the product of OA into OB remains constant. Like similarly we took this example in the same way how to get exact straight line mechanism. OA and OB should be constant in the same way. We'll prove this also. So when the link O1A rotates, that is the radius O1A rotates. Okay, so join CD to bisect at AB at R. Okay, here center one here, this is R center. Okay, and now from the right angle triangles ORC and BRC. Okay, that is this one ORC, the top one ORC, and then BRC, that is from here BRC, this triangle. So this long triangle and this is shorter triangle. Okay, so here, so we have OC square is equal to OR square plus RC square. Okay, that is by Pythagoras theorem. You know the diagonal square is nothing but other two sides square. Okay, so same thing OC square. So OC is the diagonal here like this, and OC square is OR square plus CR square, that is RC square. And similarly from this triangle, shorter one, this will be the diagonal. So diagonal is here BC. So BC square is equal to RB square plus RC square. Okay, so get okay, so what will be getting here? From this 2, subtracting equation 2 from 1. Okay, so OC square minus BC square if you do, and this one, this is which is having common will get cancelled. RC square is common. Okay, then it becomes OR square minus RB square, and you know that using mathematical relation A square minus B square, you get A plus B and A minus B. So OR square minus RB square is OR plus RB, then OR minus RB. Okay, and this can be nothing way, can be getting this in the form of OB into OA. Okay, OR plus RB is what? OR plus RB is a nothing but OB. OR plus RB is nothing but OB. Then OR minus RB, that is OR minus RB is what? It is nothing but OA, this distance, because this is subtracted. Okay, so OC square minus BC square will be nothing but OB into OA. Okay, so since OC and BC are of constant length, therefore the product of OB into OA remains constant. So hence the point B traces a straight line perpendicular to diameter OB. Okay, so we are getting a straight line here. Okay, so let us see the animation. Can see there? Can you see the video? Hello?
Yes, sir, visible.
Okay. So you can see there how the linkages are made such a way that if you try to move this, you'll be getting a straight line. Okay, this is having the rotation here, and this will be helping in a straight line. Okay, so like this you can construct the mechanism to obtain a straight line. Okay, so next this was completely exact straight line. Next we'll go to approximate straight line motion mechanisms. Okay, approximate straight line motion mechanism, we'll see some mechanisms now. So let us see the first one. First one is Watt's mechanism. Okay, so Watt's mechanism already was studied in the earlier inversions. I had shown you the Watt's mechanism. Okay, so it is nothing but a crossed 4-bar chain mechanism. In that 4-bar mechanism you had seen this, and was used by Watt for his early steam engines to guide the piston rod in a cylinder to have an approximate straight line motion. Okay, this was used in the early steam engines. So you can see the figure. So figure is clear there. Can you see the figure?
Yes, sir, clear.
Okay, so just observe the figure now. The connection is very simple. The mechanism is from having 4 links, that is here. In this manner the 4 links are connected, that is having name OQ. Okay, so OQ, OA, QB and AB can be seen in this link, and OQ is the fixed link, and then the links OA and QB can oscillate about centers O and Q respectively, and P is a point on the link AB such that PA by PB equal to QB by QA, and for small oscillations of OA and QB, P will trace a straight line. So this is going to rotate and you get the straight line in this path. So already I had shown you the animations in the earlier classes also. So I'll just once again show you. From this you can understand more clearly. So you can see this is a type of Watt's mechanism, only straight line. So point P, that is made a straight line in red color, you can see. Next you can see the another same way in the other, you can see is the straight line, the center when made to oscillate, it is a form of straight line, you can see the path. Okay, so this is regarding the Watt's mechanism. Next we'll move to next one, that is Robert's mechanism. So it is also a 4-bar chain mechanism, which is in its mean position has a form of a trapezium. Okay, the shape here looks like a trapezium, so they have given as a trapezium shape. And here,
Sir, PPT is not visible, sir.
Okay, just I think I forgot to share. Okay, so now
visible.
Okay, so in this you can see it is a 4-bar chain mechanism. Okay, type of shape of a trapezium. So you can see OA, B, OA, O1. Okay, so here in this case the link OA and O1B. Okay, OA and O1B, this one link and this link. okay, are equal length, and O01 is fixed. That is from here O01 is fixed from the lower side. Okay, and a bar PQ, here this is the bar PQ, center one. This PQ is rigidly attached to the link AB. This link is attached to link AB. Okay, and what will happen here in this case? The which bar in this, if it is attached to this link, what will happen? So this is at the middle. Okay, so little consideration will show that if the mechanism is displaced from this point, okay, you can see the pink dotted lines. That if this is displaced to this motion, that is A to A dash, if it is moving from A to A dash, and automatically B will move from B to B dash, okay, and this P will come to P dash here, okay, and when this is oscillated at this point, what will happen? The Q from the down locus of Q can be seen, it will move in a straight line. This is the straight line. Even this is motion, automatically Q will have the Q dash, it will be in the straight line, whether left side or right side, the motion will be continuous. Okay, so the point Q will trace out approximately a straight line. Okay, so this is known as a Roberts mechanism. Okay, so very simple mechanism, just a connection of P from the center, if it is at the middle of this AB, automatically you get a straight line. Okay, so let us see the mechanism. Okay, can you see this video?
Yes, sir, visible.
Okay, see there. What you can see? So you can see the link is made such a way that if the center point, if you take a straight line here, it is passing a straight line with the help of this link. Okay, just see this. Approximately get a straight line by just the motion. So depending on your applications, just make some mechanism for moving in a straight line, and automatically you'll be getting the straight line. So move to the next one. Next, Scott-Russell mechanism. This is also straight line mechanism, and we are all discussing about approximate straight line. Okay, so if the question is asked, explain any two approximate straight line mechanism, you can explain any one, any two from that, one or two. So no need to study all mechanisms. So at least two you can study. Okay, so I listed some 3 to 4 mechanisms. So this is White mechanism, and this is Roberts mechanism, and then we have seen about the next we'll see about Scott-Russell mechanism. Okay, so in this Scott-Russell mechanism, you can see the figure. So this mechanism consists of 3 movable links, that is OQ and PS and the slider S. Okay, this is OQ, this is not movable link. Okay, and PS, this entire link, PS is the entire link, and S is the slider. Okay, so slider, this S will move along the path in the form of OS. In this slider is moving in this horizontal direction. Okay, and OQ is the crank. You can see the input given here, arrow mark. So OQ is the crank, and the links are connected such that OQ, okay, OQ is equal to QP equal to QS. So all this length OQ and QP and then QS are equal. Okay, and it can be proved that the P moves in a straight line. So this P path moves in a straight line perpendicular to OS, that is perpendicular to this OS, it moves in a straight line as the slider moves along OS. So when this slider is moving in this manner, automatically P is going to trace the straight line. Okay, so let us see how it will move. So when a circle is drawn with the center Q, so you can see this Q is nothing but the center of the another circle there. You can see the dotted line given there, and diameter as PS, this entire diameter as PS. Okay, the point O will lie on the circumference. So this point O is made as circumference now, and therefore angle POS, okay, angle POS is a right angle. You can see angle POS is a right angle. So this is true for all position of S and is possible only if P moves in a straight line perpendicular to OS. So this is going to move motion automatically. This is having the path on this slide, this is going to slide, and this move in the exactly vertical straight line direction. Okay. So note that in such a mechanism the path of P is through the joint O, which is not desirable, and this can be avoided if the links are proportional in a way such that QS is the mean proportional between OQ and OP. Okay, so that is will be getting OQ by QS is equal to QS by QP. So like this we can be attained. So let us see the animation, you can understand more clearly. Okay, see here, video is visible.
Yes, sir, visible.
Okay, see once again. So this is, you can see it is moving in straight line. This is a slider, the slot is moving in straight line, but this entire motion you can see in the form of straight line. Okay, so you get to achieve the straight line here. So whenever you want a path in a straight line, you can use this straight line mechanisms. So you can see the path, black color. The slider is going to slide here and get the path in a straight line.
This is a model representing the Scott-Russell mechanism.
Okay, so you can see how the model is being made.
In which one sliding.
So for demonstration purpose, you can also create like this. In your home only with small materials, you can create this type of mechanism. You will get a straight line.
This mechanism
Okay,
has
so try to learn the mechanism and use it also. Okay, so you can create your own mechanism by constructing some linkages with waste material. Okay, so next we'll see. Last we'll see one more approximate straight line mechanism. Okay, so that is Chebyshev mechanism. Okay, name after the scientist only. So this is again approximately you will get a straight line. So it consists of 4 links. You can see the figure. The screen is visible. You can see the screen, right?
Yes, sir, visible.
Okay, I shared it. Okay. So you can see 4 links. First you can see the link OA. Okay, so OA from here. Then QB. Okay, this one from here, right side to here, QB, and then AB here, which is fixed here, AB, A to B, and OQ. OQ is fixed from the bottom. Okay, so what they have made? They have made it crossed. Okay, just same link quadrilateral only, but they have made it crossed. Okay, so it is joining by OQ crossing, and QB is crossing here, and then AB is connected in this manner. Okay, so OA equal to QB. OA is equal to QB, but they are crossed. Okay, and then P is the midpoint here of AB. P is the midpoint of AB, which is a tracing point. Okay, and the proportions of the link are taken in such a way that A and B lie in a vertical lines when they are on extreme position, and again the link AB is half of OQ. Okay, the AB is taken as half of OQ, and you get the ratio AB is to OQ in the form of 1:2, and AB is to OA, you get 1 is to 2.5. Okay, so this shows a path in the move in a straight line. So you can see A will move from A to A dash, then automatically B will move to B dash, okay, and this P will move to P dash. Okay, so the point P moves approximately in a straight line parallel to OQ. Okay, so this will move in a straight line parallel to OQ. So P, you can see P to P dash and P double dash is also shown here. Okay, so move parallel to OQ. So last what you had seen perpendicular. Now this here you are getting the parallel. Okay, so let us see the animation. Okay, can you see the screen?
Sir, visible, sir.
Okay. So you can see the cross. The links are arranged in the spaces. It is a crossing. So you can see the center point, how it is making a straight line. See, without animations you will not be able to visualize. So I am showing you the animations. So we will give you the clear idea. Just by 2D figure it is very difficult to understand. So you can see it is again approximate. You will not get exact straight line. It is approximate straight line.
In this mechanical video I will explain how to Chebyshev straight line generator work. As you see, it is 4 bars linkage type. What is special? Purple
just
bar can
see
rotate
how
around
if
yellow
the
pin.
links are arranged in little bit different manner, you will get different types of
Blue bar
motion.
can rotate around red pin
That is the
follow green link and
specialized
pink
uses
pin that
usage
follow
of
purple
how
link.
the links can be connected, how
Green
mechanism is
bar
going
can
to work.
rotate around
So you
orange
can see
pin.
with just 4 links how
Pivoting
different
purple
types
and
of
green
motions
can
can
only
be
oscillate.
created.
Length of purple
This is the
link and
beauty
green
of
link is same.
studying the mechanisms.
Mid pointer of link blue
Okay. So you have studied different straight line mechanisms. Okay, so this is again one of the straight line approximate straight line mechanism. So let's will continue. Okay, can you see the screen?
Yes, sir, visible.
Okay. So these are the 4 to 5 straight line mechanism you can study. Okay. So next we'll see the other mechanisms which are there. Okay, pantograph I think is not there for your syllabus. Okay, but still I'll just show you some consideration. You can see the pantograph is an instrument used to reproduce to an enlarged or reduced scale. Okay, suppose you want to reduce or enlarge some scale. Okay, suppose you draw small and you want to enlarge it. So that is you done by help of pantograph. Okay, so actually this is not there for your syllabus, so you don't need to study. Just I will for your information I will show you. So you should know this. So it used in a different top side of your engine, trains. So at the top, how to connect the to electric lines. This is used. You can see for the as drawing purpose also, to draw in the reduced scale or larger scale. Again, this are used. Okay. So I will not go much depth in this. So used in the reproduction of plane areas and figures such as maps, plans, etc. for enlarged and reduced scales. Okay. So again these are used also in guiding the cutting tools. Okay. So mainly again also used in the form of collect the power at the top of the electric locomotive. Okay. So this type of pantographs are considered. So just good. Next we can see the toggle mechanism. Okay, this is also not there for you. Okay, don't study toggle mechanism also. But they are again toggle mechanisms are used where large resistance are to be overcome with a short distance. Okay, in this you can see this is a shorter link. If only with the small motion of this, okay, with the what will happen? This entire P is going to push over here, and this getting the sliding motion at point E here. Okay, so large resistance are to be used to overcome short distances. Okay, so this type of mechanism is used. These are miscellaneous mechanisms used in rock crushers, pressers, riveting machines. Okay, so this is a toggle mechanism. Okay, so just for your information, you can study this extra too. No need to actually study for your exam. Okay, so just will stop here.